Okay, this is one I think we can go a little bit faster on. We're just going to do a lot of reactions. We're going to add a lot of review. And we're going to add a few more atoms. So esters. What's an ester? What is an ester? Aha. Okay. So an ester is something that looks like that, right? There's your ester moiety. Okay. So esters can also undergo reversible condensation reactions, right? Because they're going to have alpha hydrogens, right? So let's go back to red. They can also, so it's gonna be the same thing. Well, there's a slight difference, but watch this now. So that first of all, you've got your alpha hydrogen here, okay? You deprotonate it, proton transfer, bam, and you get your enolate, which looks like an enolate, right? Except we've got this thing over here that's different. That's the only difference right there. This is resonance stabilized with another structure, which you have to put when you're drawing the mechanisms. Big deal, really matters. Now we've got our nucleophile, right? This looks like chapters 19 and 20. So these electrons come over here, bam, bam, okay? Looks just like chapter 19 and 20, and we get this, okay? Now the difference is that we now have a leaving group. Right, before we just had another carbon there, or a hydrogen, when we were doing aldehydes and ketones. We now have a leaving group, okay? And there it is, right there. You've seen leaving groups like that before. What's the name of that leaving group? What's the name of that leaving group? Say it out loud. What's the name of that leaving group? It's an alkoxide. Okay. So we know what's going to happen, right? We're going to get these guys that come back down, and we're going to get a leaving group. This is just like chapter 20 and 21, right? So we have an addition, nucleophilic addition, elimination. We've seen that before, okay? All right, and sure enough, there it is. There's our elimination step, right? So you see boom, and then boom, okay? And that's concerted. It happens at the same time. So the carbonyl group is reformed. And when that's reformed, you have an alkoxide in solution. So here's your alkoxide. That's your leaving group, right? You see it? It's right there. Okay? Well, this is a pretty good base. And we know that this is actually a decent acid. We learned that its pKa was probably, I don't even know, pKa around 9? Oh, wow. Okay, so that's very readily going to get rid of that hydrogen. Okay? So in order for that to happen, this alkoxide is going to come and take it, and we get rid of that. This is resonance stabilized. If you draw the mechanism for this, you have to draw the mechanism for this. You need to draw this. What is there's actually a couple, right? Oh, I don't know how many there are. Okay, so draw the resonance structures of those. The resulting doubly stabilized enolate. Now we have another enolate, right? It must be treated with an acid in the last step. It has to be treated with an acid in the last step. Why? I hope you answer these questions. Why? A beta keto ester is formed. All right? So we have our alpha, beta, right? So we've got a beta keto ester, which is formed. All right, there are some limitations to the Claisen condensation. First of all, the starting ester has to have 2 alpha protons. It has to have 2 alpha protons. If that doesn't make sense to you, stop the video and draw out an ester with 2 alpha protons, and draw an ester out that doesn't have 2 alpha protons. Okay? Because removal of the second proton by the alkoxide ion is what drives the equilibrium forward. All right? Hydroxide, and here's the reason why. Because we have to draw, if we're going to make the reaction happen, that's essentially what that means. It's not going to go forward if it doesn't have the second proton removed. Okay? Hydroxide cannot be used. Why can hydroxide not be used? That would be a great thing. Draw the mechanism out for hydroxide being used. Wow, that's a good question. Draw the mechanism out for a hydroxide being used. What would happen? An alkoxide equivalent to the OR group of the ester is a good base. All right? So what is an alkoxide equivalent of that OR group? What is it? Okay, now go practice with conceptual checkpoints 22.28 and 29. I think this might be the last slide here. No, we have a couple more, sorry. Okay, so cross-Claisen reactions can also be achieved using the same strategies employed in crossed aldol. Strategy one, where's my marker? Strategy one, we have one that has no alpha hydrogens. Okay. And another where we first of all make the enolate first, and then we drip this stuff in. That was method 2. Make this stuff first with LDA. If you don't have this memorized yet, draw the structure out now. What is the structure of LDA? Okay, and this is what you get. All right, and we treat this with an acid. Gives what? Now go practice with conceptual checkpoint 22.3. And I think this may be the last slide. I don't remember. No, one more, sorry. Okay, intramolecular. Oh, of course. Intramolecular Claisen reactions can also be achieved. All right, so now this is called a Diekmann cyclization. How did I forget this? This is called a Diekmann cyclization. Proceeds through the expected 5-membered ring transition state. Draw this. Draw it out. Draw this mechanism out. Okay, and bring your notes with you to class. Well, I'm going to say it again. I think this might be the last slide. Okay, practice with conceptual checkpoints 22.31 and 32. And good luck to you.